In this last video, in the sort of the compounds and molecules section, we're going to go into the naming of various compounds and the rules associated with naming compounds. Incidentally, as a side note, you may have noticed that for the most part, these videos that I make, these lectures, pretty much coincide with the various sections in your textbook, unless I feel it makes more sense to break it up a little bit, and that's what we're really doing here. The naming in your textbook is really sort of wrapped up into the various sections. But it makes sense to me to break it out and have it as its own lecture. Because that's what this lecture is all about, is how we name compounds. There we go. It's very important to be able to have a systematic and normalized way of naming chemical compounds, because what we need to be able to do is to find the formula of a compound from the name. And we're going to start out with ionic compounds. And so in an ionic compound, if I give you the name of something, you need to be able to then come up with the chemical formula of that. And so there were those two examples there, but let's just look at those. So for instance, if you have the name of, actually we'll mix it up a little bit. If I give you the name sodium bromide, then we need to be able to come up with a chemical formula. And we know from this name that, okay, we have sodium. We look on the periodic table, we see that sodium has a 1+ charge. Bromide is the ion of bromine, and we'll talk about the IBE in just a second. Bromine has a 1- charge, and so my chemical formula is going to be NaBr. What about sodium sulfide? Again, Na with our 1+ charge. We look on the periodic table, sulfide with its 2-. So that tells me that the chemical formula for sodium sulfide is going to be Na2S. And so we need a way to name compounds that is very common, is very systematic, so that we are able to come up with those names, or sorry, with those formulas. And the rules are pretty simple when it comes to these types of compounds here with ions that have very predictable charges. What we do for these, the name, and so let's go back the other way. If I have, sorry, I wanted to write the actual formula. And so let's say I have MgCl2. And so just like in the formula, our cation is going to come first. The ion of the cation has the same name as the element. And so Mg is magnesium. And so the magnesium ion is also simply magnesium. Anions, however, we do change slightly. And so this chlorine as an atom, so chlorine, when it forms an ion, it's chloride. And so we break off the end and we add IDE. And we do that with any negatively charged cation, or negatively charged anion, sorry. And so MgCl2, the name is going to be magnesium chloride. And that's it. That's all that we need. Because we're able, if I give you this name, you would be able to come up with this chemical formula. Excuse me, just from using the charges that you can find from the periodic table. So we can look at another couple examples. If I have, let's say, potassium, sorry, we're trying to come up with the names here, so I should be writing the formulas. Did it again. Let's say I have K2O. K is potassium. O is oxygen, which we shorten to oxide for the ion. So we have potassium oxide. CaBr2. Ca is calcium. Br is bromine, which changes to bromide. And that's it. We would be able to go back and forth between the name and formula for each of these easily. Now let's talk about if we have a transition metal, though. Transition metals start to get a little bit stickier. Let's say that I tell you we have the compound iron oxide, and you need to come up with a formula for that. I've already told you that the transition metals, remember everything in the middle here, and there's iron right smack dab in the middle of those transition metals. Those can have variable charges, and there's no way to tell their charge just from looking at the periodic table. Iron, I will tell you, could be either a +2 or a +3. And so if iron is a 2+ and oxygen is always going to be its 2-, then we come up with a formula FeO. If, however, this happens to be iron 3+, then we get the formula Fe2O3. So just from the name iron oxide, there is no way for you to tell which of these I'm actually talking about. And so anytime that we have a transition metal in a compound like this, in an ionic compound, we have to identify what the charge is on that transition metal by using Roman numerals. And so iron, this one was formed by using the iron 2+, and so its name is going to be iron 2 oxide. Probably predict what this one's going to be then. Iron 3 oxide. And that's what these slides are all about here, is using those Roman numerals in order to identify what the charges are going to be. Now, if you're going back the other way, what you might have to do is use information that you know to figure out what the charge is. So for instance, the compound MnO. Oh, there we go. The compound MnO. Oxygen's always going to be a 2-, no matter what. That's not going to change for us. And so here we see that we have one of each. This means that the charge on this particular manganese ion must be 2+. And so the name of this is simply going to be manganese 2 oxide. So we're using the information we know. We're using the fact that we know oxygen is a 2- in order to figure out what the charge is. Let's look at another example. If I have the compound FeNO3, 3, I recognize nitrate as my polyatomic ion, NO3, which has a 1- charge. Now I have 3 of these 1- charges, and I only have 1 iron. This tells me that the iron must be a 3+. So we get iron 3 nitrate. And we'll talk about this polyatomic naming in just a moment. But again, that's why it's important to recognize your polyatomic ions. So here's another example here. So Cr2O3, again, remembering that oxygen is always 2-. Here I have 3 oxygens. That'd be a total of -6. I have 2 chromiums. So I need to get to a +6 with those 2 chromiums. And so each chromium must be a +3. Chromium 3 oxide. Cr2O7. Chromium can be a whole bunch of charges. Chromium's wacky like that. So Cr2O7. O7, oxygen's always -2, so that's going to get me to a -14. I have 2 chromiums. Those 2 chromiums have to add up to a +14 to balance out the oxygen. So each chromium must be a +7. We get chromium 7 oxide. There are some exceptions. Silver, cadmium, and zinc are actually ones that will never change their charge. Silver is always a +1. Cadmium and zinc are always a +2. So for those, we don't actually have to add in the Roman numeral because there's no variability. They'll never change. So AgF, we can simply name as silver fluoride. ZNO, it's just going to be zinc oxide, and so on. If you have a compound with a polyatomic, let's talk about naming rules for our polyatomic compounds. Those are simple. The name of the polyatomic ion is simply the name. Use it. And so NaNO3, sodium nitrate. NO3 is our nitrate ion. FeNO3, we already went through this one. So that's iron 3 nitrate. We have to include the 3 because iron is a polyatomic, is one of our transition metals. Na3PO4. PO4 is the phosphate polyatomic ion, sodium phosphate. NH4, there's our only positively charged polyatomic ion. That's ammonium. We get ammonium chloride. Go ahead and try these. There's a mix here of just standard sort of binary compounds. There's some transition metals. There's a couple of polyatomics in here. Pause the video now, give these a try, and see what you can come up with. Pause the video now, try these out, and see what you can do. Hopefully you got these following names. If you didn't, go back and look at what we've talked about. Try them again. Try to see where you went wrong. So now let's talk about naming covalent compounds. So covalent compounds, as we've mentioned briefly, there's a lot more flexibility in how they come together. And so if I have something like, for instance, if I give you the name, back to ionic for a moment, but if I give you the name calcium bromide, calcium's always a 2+, bromine's always a 1-. So CaBr2 is always the way those are going to come together, no matter what. That's not going to change. And so just the name calcium bromide gives me enough information to come up with that formula. With nonmetals and covalent compounds, it's not that simple. Let's say nitrogen and oxygen are coming together. Nitrogen and oxygen can come together with just one of each, NO. We could have NO2. We could have NO4. We could have N2O. We could have N2O4. We could have N2O5. There's just a ton of variability because once we start to share electrons, there's more versatility in the combinations that they're going to be able to come together in. So simply saying now, nitrogen oxide does not give me enough information to let me know which combination we're talking about. And so with covalent compounds, we need to specify the number of each atom by using a prefix. So if there's 1, we're going to use the prefix mono, 2 di, 3 tri, and so forth. Most of these are probably ones that you're semi-familiar with. Tetra, you might not have heard, and maybe nona, maybe even hepta, but most of these you're pretty familiar with. They're the standard number prefixes that you've seen in other places. And so we put that prefix in the front of each element to indicate how much of each that there are. One exception is if it's only one of the first element, you do not need to put mono in front of the first element. That's the only time that you would not use the prefix. That's bothering me. There we go. So CO, carbon monoxide. CO2, carbon dioxide. Di indicating we have 2 of the oxygens. So a few more examples. BCl3, boron trichloride. 1 boron, but we don't have to put the mono, and 3 chlorides, trichloride. SO3, sulfur trioxide. NO, nitrogen monoxide. And just note that we write it as monoxide. We kind of get rid of one of the O's there. Monoxide, not monooxide. N2O4, dinitrogen for our 2 nitrogens, tetroxide. So try a few out. Try to come up with the formula now from the names of these. Boron trichloride, is BCl3. Sulfur dioxide is SO2. Silicone hexabromide, oh, there it is, went a little too fast, SiBr6. Diphosphorus pentoxide, P2O5. Now, as a note, so you only, let me come back a ways here. Here we go. You will only ever use these prefixes for covalent compounds. If you use these for an ionic compound, it is incorrect and it will be marked as such. So if you have MgCl2, and if you name this magnesium dichloride, that is wrong, and it will absolutely be marked as wrong every single time. These naming rules are incredibly specific. We only use these prefixes in the case of covalent compounds. Lastly, naming of acids. We're going to talk a lot more about acids and bases in a week or two from now. But just we're going to look at some of the naming conventions. One of the generic ways to think of acids is that acids will give off H+. They'll give off a hydrogen plus ion when they're dissolved in water. And so a generic way to write it is just HX, where X could be really any sort of anion, any sort of negatively charged ion. Very commonly, X might be one of our halogens. So our halogens here in our group 7, fluorine, chlorine, bromine, and iodine. Also technically acetine, but acetine, nobody ever talks about it. So fluorine, chlorine, bromine, and iodine. So if the anion is one of those, what we call a halogenated acid, then we name the acid by saying hydro, and then the root of that halogen. So in the case of HCl, hydro, chlor, and then ic at the end. So hydrochloric acid. If it's HBr, hydrobromic acid. If X happens to be one of our polyatomic anions, then in those cases, if the end of the polyatomic ion ends with 8, then we call it ic acid. So for instance, NO3 is nitrate. So we would call this nitric acid. PO4 is phosphate. So we get phosphoric acid. If the end of our polyatomic ion ends with ite, then that's us acid. So NO2 is nitrite. So that becomes nitrous acid. Now that's a lot of different naming rules. There is a naming worksheet or a naming handout right on the website. This does not include acid naming, but it does have the rules for ionic and covalent naming. So there's a resource that will help you. There's also this flow chart that I came up with a year or so ago, which will help you just sort of go through the whole thing. And so asking yourself first, is it an ionic or covalent? Go from there. Is there a metal or an NH4? And so now you're starting to go from there, and that this will lead you through all of the rules. The flowchart is also separately found right on the website. And so this is something that might help you just sort of flow through things a little bit, asking yourself these questions, leading you to eventually the various naming rules that you'll want to use to name your compound. And so that's it for our naming of compounds. And so, as always, thanks for watching, and you stay classy, USM.